Now that was the first part of the presentation where we were just getting familiar with the basics of a chemical equation. Now we're ready for learning how to count atoms and preparing for this task of learning to balance chemical equations. So this next part is called counting atoms. Chemical equations are supposed to accurately reflect what's taking place in a reaction. Remember, in a chemical reaction, matter can neither be created nor destroyed. So what this means in writing chemical reactions is that the same elements have to be present both in the reactants and the product side of the reaction, and that the number of atoms of each of those elements also has to remain constant during the reaction. Because these are ordinary chemical reactions, we don't have matter changing from one type to another. It's not a nuclear reaction. So if I start with 2 atoms of hydrogen, I need to end with 2 atoms of hydrogen. If I start out with 1 atom of oxygen, I need to end with 1 atom of oxygen, etc. To ensure that this is the case requires counting the number of each type of atom on the reactant side and on the product side. And these two counts should be identical if the chemical equation is written correctly. In order to do this, we begin by understanding the role of subscripts in formulas, as well as coefficients that you will find in balanced chemical equations. So we'll start with the role of subscripts. Recall that the subscripts in a formula can tell us the number of atoms of a particular element in one unit of that substance. So as this is written here with NaCl and AgNO3 as my 2 reactants, we can see that in NaCl that there is just a single sodium atom and there's a single chlorine atom. We can see over on the other side with the silver nitrate that there is 1 atom of silver and 1 atom of nitrogen. But that 3 after the oxygen indicates that there are 3 atoms of oxygen. What happens when there are parentheses in the formula followed by a subscript? Recall that parentheses are put around polyatomic ions at times. They're put around there when you're trying to say, I have more than one of these in this formula. So you'll see a subscript outside the parentheses telling you how many of them you have. So in this particular case, you see NO3 in parentheses, and the 2 outside means that we have 2 of these NO3s. So it's like having NO3 plus another NO3. And it's clear to see from this that we have 2 atoms of nitrogen, 1 in each of the NO3s. Hence the 2 for our count of nitrogen. Now, we also see that we have 3 atoms of oxygen in each of these. That's a total number of 6 atoms of oxygen from Ba parenthesis NO3 parenthesis 2. Now, this count can be arrived at without having to write NO3 twice like that. We just need to remember to take the subscript outside parentheses times the subscript of each element in parentheses. So the subscript on N is understood to be 1, so we would take 2 times 1 to get 2 for the total count on nitrogen, and 2 times 3 to get 6 for the oxygen. Looking at just the reactant side of this reaction, we are going to identify the atoms of each type shown here. So in FeSO4, we have 1 of the irons, 1 atom of sulfur, and we have 4 atoms of oxygen. Over here on the other reactant, we have 1 atom of barium, but be careful that N, we have to take its subscript of 1 times 2, so we have 2 atoms of nitrogen, and we have 6 atoms of oxygen. Now, sometimes the same element shows up more than once in a particular formula, such as in the formula for ethanol in the following combustion reaction. C2H5OH plus 3O2 yields 2CO2 plus 3H2O. Notice in C2H5OH that I have 2 carbons. But be careful, I don't have just 5 hydrogens. Hydrogen appears in that formula twice. So I have 5 to begin with and another one mentioned later on. So we have 6 of those and 1 oxygen. This is easy to count in the pictures shown to the right. Now, this reaction also contains large numbers in front of some of the formulas. Those are called coefficients. These are just whole numbers telling us how many units there are of a particular substance in a particular reaction. To understand that 3O2 means that there are 3 molecules of oxygen, we can look at the following diagram. So 3O2 molecules means that I have, as shown here, 3 oxygen molecules. And so if you count, you will see that 3O2 means I have O2 plus O2 plus O2, and so there are 6 oxygen atoms. This means that if you know the number of atoms in one unit of the substance, what you need to do is multiply that number by the coefficient of the formula to find the total number that are represented as taking part in that reaction. So 3O2 means there are 3 times 2, or 6 oxygen atoms. 2CO2 means that there are 2 times 1, which is a total of 2 carbon atoms, and 2 times 2, or a total of 4 oxygen atoms. If we put all of this together, we're going to count the number of each type of atom indicated by each of the following. So 4H2O. Well, first of all, I have 2 in this formula, but I have 4 of these molecules. So 2 times 4 is 8. 8 atoms of hydrogen. Oxygen, I only have 1 in the formula, but 4 of those units means I have 4 oxygens. In diphosphorus pentoxide, there's 2 phosphorus, but 2 molecules of that means my phosphorus has 4 atoms total, and my oxygen with 5 in each molecule, followed by 2 of the molecules, then that's 10. In my next one, I have 3 substances. I have barium, I have nitrogen, and I have oxygen. Looking at the barium, there's only 1 in that formula unit, but I have 3 formula units, so 1 times 3 is 3. With the nitrogen, I have 1 in that polyatomic, but then there are 2 polyatomics, so that's 2 nitrogens. But wait, I have 3 formula units of it, so I'd take 2 times 3 and get 6 nitrogens. And then oxygen shows 3 as its subscript, but I have 2 of those polyatomics, so that would be a total of 6 in a formula unit, but I have 3 formula units, so 3 times the 6 is 18. And then finally, our challenge molecule. This one's a challenge because if you notice, each element is actually appearing twice in this formula, so you need to be careful and make sure you get them all. So we have 3 elements, carbon, hydrogen, and oxygen. There's a carbon at the beginning with just a subscript of 1 understood. Same thing for the next carbon, understood to be 1. So really there's 2 in this molecule, but I have 2 molecules. So 2 times 2 is 4. With the hydrogens, I have 3 at the first part, but then another 1 later on. So that's 4 hydrogens in that molecule. Times 2 gives me 8. And of course, oxygens. I can see that I have 2 there. And so then if I have 2 of these molecules, I have 4 total. I hope that you have found this to be helpful and you can join us for the next one of these presentations.